couple of exponential equations and then log?
Yes, please.
Yes? Okay. So, Tim, if you'd like, I missed all of you. I really did. It was heartbreaking for me. From 1 through 48.
No, no, this.
Oh, she really missed you.
I did.
She missed you.
I did, all of you, not just him. He's my torturer, and that's why I have to miss him. But he's been my torture for a year. 2 years. Okay, 3 years. Okay, so let's choose. Now, one type that I would like to present and I did not see in the notes is, for example, problem 42. So 7 raised to 2x plus 1 equals 3 raised to x plus 2. This is not a very easy, it's not difficult, but I would say it's more cumbersome. It's a long process of solving this equation. Now, we already know the simple exponential equations, like, for example, 2 to the x equals 2 to the third. Two numbers are equal and they have the same base. What has to happen to the exponents? They have to be the same. No question there. Correct? But here, I don't have the same situation. I see 7 as the base, and I see 3 as the base. So the problem is 7 and 3 cannot be presented with the same base. Right? Okay, so then this procedure does not work here. We know that log is the only function that has 3 properties. No other function has these 3 properties. One property is log applied to a product. Right? You remember that from last time? If you say no, I'll repeat those. Yes, you add the logs. The second property is log applied to a ratio. Difference of logs. And the last one, log applied to a power, and the number goes in front as a factor. Right? Okay. So whenever I solve this equation, forget about this one for a moment. If I have the square root of x equals 4, how do I solve this equation? In other words, how do I get rid of this? Exactly. So I'm using the operation that is the inverse of the square root. Okay. So now in this equation, the concept is the same. I have to apply, like I applied here, power 2 to both sides. Here I have to apply a function that brings this number in front down as a factor. And there is only one function that does that. And it's not the square root, and it's not a power, but it's what? It's the function called log. So if two numbers are equal, their log will be equal. Their logs will be the same number. So if two numbers are 5, log of 5 and log of 5 will be the same. So if this side equals this side, log of this side in the same base will equal log of this side in the same base. Because the two numbers are equal. Their logs will be the same. And why am I applying log and not squaring or who knows what? It's because I want this power to be brought down in parentheses as a factor. And this is the only function that does that. No other function will. Besides, this function, log, is the inverse of the function exponent, exponential function. So I have to apply the inverse function like I did here. I had the square root, and I apply the inverse function. Same thing here. I have the exponential, and I apply its inverse function, which is log. Good. So can anyone dictate the right-hand side? In parentheses, mandatory. times log 3. Any questions? Okay, so now, what do I do next? Remember, I'm solving for x. Correct, but first I have to distribute. I'm distributing this fancy number, log 7, and log 3 to these two terms. Can anyone dictate the next step, please? What will I write? 2x log 7. We do not put log 7 or the square root in front of anything. It's not a mistake, but we want to make sure that we don't make an assumption there. Plus log 7 equals very good, log 3, very good, plus 2 log 3. I have to distribute to all terms. Very good, awesome. Is this clear, everyone? Yes? Okay, now remember we are after x. I see x in this term and I see x in this term. What do you recommend we do? Yes, I move this term here and I move this term next to the other one with x. Indeed. 2x log 7 minus x log 3 equals 2 log 3 minus log 7. Very good. Okay. Now what? Always remember the keywords in algebra. Factor simplify, factor simplify, factor simplify. So, remember I'm after x. Can I combine these two?
Yes.
They're not like terms. I cannot combine them. So then there must be something I can do. Very good. What am I factoring? Awesome. Very good. Perfect. So, awesome. What is left in parentheses? Very good. 2 log 7 minus log 3. Final step, x. Very good. Awesome. Yes, exactly. So 2 log 7 is in the denominator minus log 3, and the top is 2 log 3 minus log 7, indeed. Perfect. Well, this was the most difficult. Why? Because I didn't want to evaluate these and introduce a lot of error, so I had to keep it separate till the very end. Now, if you want, you can simplify it with a graphing calculator. If you want to approximate and see what it is. So go to y equals, okay, in parentheses around the top, always parentheses around the top, 2 log 3 minus log 7, close parentheses, don't forget parentheses around the numerator and parentheses around each and every log of the number, okay? Now divided by, in parentheses, and we have 2 log 7, close the parenthesis, and then minus log 3, close, and enter, and it's 0.08997 approximately. How do I check my work? Okay, here's how I check my work. Please pay attention because I think it's useful to know. Here, so I have 7 to 2x plus 1 equals 3 raised to x plus 2. I prefer checking this equation, and I want you to tell me if it's the same equation with the 1 at the top. Would you tell me whether this equation is identical with this one? Because if this one is not identical with that, I cannot check in here. But if you say they are the same, then I prefer checking in here than in the top. They are the same. All I did was I moved one term from one side to the other. Of course. Very good. So I'm going to check it in here. So now with a calculator, I have 7 caret in parentheses 2 multiplied by the previous answer. Do not delete what you had in the calculator. So 2 multiplied by the previous answer, and the calculator will take the whole thing, not just pieces of it. Okay, plus 1. And then close the parenthesis, go outside, minus 3 caret in parentheses, x plus 2, but x is the previous answer, and then plus 2, and close the parenthesis. One more time, if this is the correct answer, when I click enter, what should I get?
0.
David, you said something?
Right.
No, it's 0. Otherwise, the solution is incorrect. So then I can say now that all my calculations, all my work here is fine, and this is indeed the correct approximation. Okay. What did we say about exponential equations? I'm sorry, take it back. What did we say about the exponential function? Friendly or not friendly?
Not friendly.
Friendly. Exponential, like polynomials, like linear, and so on and so forth. No problems. What did we say about the log function? Not friendly. Log function cannot be defined, cannot be applied to anything but what type of numbers? Positive. Correct. Very good. So then we are now facing log equations. So what do I have to worry if the log is not a friendly function? What do I have to worry when I solve log equations, which I did not have to worry when I solved exponential equations? When we solved exponential equations, we did not state domain, because the domain is all real numbers. We didn't have to worry about any of that. Good. But now with log equations, I have to be very careful, because it's like a square root. When I solve radical equations, I have to go back and check. Right? It's mandatory. And so on and so forth. Rational equations, I have to have restrictions. The denominator cannot be 0, right? And the same thing with log equations. Okay, so let's take a look. Let's start with problem 70. On page 515. Log base 6 of x plus 3 minus, I'm sorry, not minus, but plus, log base 6 of x plus 4 equals 1. Is this a log or exponential equation? Of course, because it has log in it. It cannot be an exponential, it's a log. Very good. Awesome. Now let's look at this function, and please tell me the domain. What will I have to write? Not tell me the domain, but tell me what I should write in order to find the domain.
Negative.
I have to write that x plus 3, which is the quantity that we apply log to, must be awesome. The domain for the other function, I have to write very good. Yes. Very good. Awesome. I have to state these restrictions before I do anything to the equation. I can't touch it. I have to state the domain first. Good. So this first one, x greater than -3. The second one, x greater than -4. I will graph these two in order to find the common territory where they both exist at the same time. Greater than -3. Here's my -3, greater than -3. As you know, I don't care for units here. This is just a tool to give us the domain. And -4 is here. -4. So where's the common domain for these two functions then? Very good. Awesome. So if I find a solution for this equation that is, for example, -10, what would you say about that solution? Say it again.
It's false.
False. So whatever I get has to be a number greater than 3. Otherwise, I will say the equation has no solutions. Perfect. So now please tell me how I condense this left-hand side. Log base 6 of x plus 3 times x plus 4. Should I review these three properties with you?
Well, you called something different. I didn't have it written down how you refer to the three different types. So go over them with your lingo.
Yes, yes. So let's do that, and I'll come back. So just allow me 1 second to I refresh your memory on those three properties, okay? Properties of log. There are three properties that no other function has. So here is the first property. Log of x times y. This is the sum of two logs. Log applied to x and log applied to y. But what is very important to understand is that this relationship is dynamic. So if I have log applied to a product, I get a sum of logs. If I have a sum of logs, they have to have the same base. I can present it as log applied to a product. So this is the product rule. So here's the quotient rule. Log x over y. What do you think this will equal to?
Log of x minus log.
That's it. Again, it goes back and forth. If I'm given the difference of two logs in the same base, I can write this. Is that okay? And here's the third one. Sorry about that. Here's the third one that we just used. Log of x raised to power b. This is the power rule. This is the quotient rule. This is the product rule. Product, quotient, power. B multiplied by log x. Again, this goes back and forth, which means if in front of a log there is a quantity, whatever that quantity is, it really comes from the power of this expression. Or if I see it as a power, then I know it goes in front as a factor, which means not addition, not subtraction, not division, just product. Product. Okay, so coming back to our equation, I am given a sum of two logs. Which of these properties really applicable here? In the reverse order, of course. The first one, very good, indeed, the product rule. So then that's why this could be changed into this, in which this quantity and this quantity are multiplied inside log. That's why this was changed into this. Or if I want to go back, log base 6 of x plus 3 plus log base 6 of x plus 4. Is this better? Okay. Now, as we discussed last Monday, when I was still doing well, any log equation can be changed into an exponential equation. How? Counterclockwise, always starting with the base. The base raised to first power equals that whole thing, indeed. So how do I write this again then? Indeed. So I changed the log equation using the change into an exponential equation. It turned out that it's even easier than an exponential equation. What type of equation is this? What is its degree? But don't I have to multiply x by x? So that is what type of equation? That's it. So how do I solve a quadratic? Right, but I have to, yes, but I have to set it equal to 0. That's all I want you to say, right? So 0 minus 6. X times x, x squared. X times 4, 4x. 3 times x, 3x. And 3 times 4, positive 12. I had to distribute, right? Because it's quadratic. I have to set it equal to 0. X squared plus 4x plus 3x plus 12. So this is x squared plus 7x plus 6 equals 0. So after all the algebra of distributing and combining like terms and set it equal to 0, then I know now I have to do what? Yeah, because it takes a blink. Otherwise, I would have used the quadratic formula. Not completing the square, of course, and not taking square roots because it's not ready for that. Good. So now please tell me what you get. So then there are two possibilities here. Very good. Not so fast, right? What is the conclusion then? Only -1. That's why we made this effort. And I will say no way. And I will say yes. If I don't state the domain and find the common domain, then I will have to go back in the original problem and check. It's up to you. If you don't state the domain, then you have to go back and check. It's up to you. Okay, let's choose another. And let's look at some word problems now. Yes, please. Yes.
So when you change from a logarithmic function to exponential function, the only reason
It basically collapsed into a quadratic.
because it's only a 1. Had it been like another number, that would have been more complicated.
It would have been 6 squared or a 6 to the third. Still would have been quadratic.
So you just put the exponent for the 6.
So the base raised to this number equals the entire
Oh
expression.
yeah, it goes back. Okay.
Yeah. So I was hoping for that. I was hoping that the equation would collapse into something very simple I can solve.
Right. And so if you see that like you have those two functions combining and it's like x plus something, like you can kind of identify what kind of problem it's going to turn into.
If it's a sum of logs, then it will be log of a product.
So
Let's look at the difference now, and we'll see what happens with the difference. Yes. Okay, on the same page, 515. So let's look at a difference. Um, 71. You can choose if you want. If you want to choose, I'll be more than happy. 71. Log base 2 of x plus 2 minus log base 2 of x minus 5 equals 3. I recommend you start with the same idea. Do not touch the equation, do not condense, do not do anything, but please tell me the domain or what I should do to find the domain for the first function. Yes? Awesome. What needs to be written for the second piece? Perfect. So the first one is x greater than negative 2, and the other one is x greater than 5. Let's look at the real line and identify where they both are true. Which x values I should pick so that both pieces exist at the same time. Greater than negative 2 is this piece. Greater than 5 is this piece. Notice that I don't care for units. This is just to give us an idea, but I have to present them in the correct order, of course. So I need to pick that piece, that interval, that make both logs exist at the same time. Say it again. Exactly. So the common domain is 5 to infinity. If there is no solution in the interval 5 to infinity, nothing else can be accepted. Good. So now let's look at, and I'm ready now, after I stated the domain, I am now ready to change this and condense it. Which property do I use? There are only 3 properties. Let me refresh, or I should say maybe re-emphasize. There is no log applied to a sum. You cannot break the log of a sum. You can only break the log of a product, ratio, and power. So if you see something like log of x minus 5, you cannot write it's log of x minus log of 5. This is not a distributive log or anything like that. So this is fixed. You can't change that. That is fixed. You can change it. But I can go backwards on one property. Which property? Yes. Perfect. So how do I write it? So this whole thing can be changed. Yes, log base 2. Very good. How did we decide to put a ratio and not a product? Because it's a difference. Exactly. Very good. Good. So now I'm ready to change this into an exponential equation. Where do I start? Where do I start? The base raised to, yes, equals? Yes. Awesome. So then 2 to the third equals x plus 2 over x minus 5. Very good. Well done. So now this is done because now I have to solve this equation. How much is 2 to the third? Or 8 over 1, and you'll tell me why I'm writing it. What is the information I'm giving you by writing it 8 over 1? Exactly. This is just for you to notice that it's a proportion, so we will cross multiply. Tim, are you okay?
Yeah.
So then this, so 8x minus 40, we have to distribute to both terms, equals x plus 2. What type of equation is this? So it was rational, and now it collapsed into even easier than quadratic. What is this? What type of equation is this now? Very good.
What did you say?
Linear. So I move x, 7x, I move 40, 42, x equals, with a question mark. Is it a yes or a no?
Yes.
It is a yes, because of this. I don't have to go back and check. It is a yes, because 6 is greater than 5. Any questions from me? Okay. I would like to finish this chapter with a couple of word problems. So all these lead up to this section, which is the last section of chapter 4. Applications. We will look at 2 applications. Actually 3. Okay. The first one, exponential growth. Exponential growth. Just leave a little bit of space right here in between. Number 2, exponential decay. A little bit of space. I'll come back in a second. And number 3, logistic function. Okay. Examples of exponential growth. Bacteria grow exponentially. So when we talk about bacteria, the bacteria will follow this model, and we'll put the model in here in a moment. What else? Populations, like people, mice, rats, bats, rabbits. So all populations. Fish, me too. I can relate to that. Fish population, and so on and so forth. All of them will follow this model right here in a minute, because I want to put both models together. Another example of the exponential decay. Assuming we would not be alive, but assuming that there is a radioactive substance right here. It's not. It's something I don't want to use. Their mass decreases in time. By decreases in time, we really say exponential decay. So a radioactive substance decreases its mass in time. So it decays. So here we're talking about number of bacteria, number of people, number of mice. Here we're talking about mass. The mass of the substance decreases or decays in time. So although your book uses the same notation for both, I disagree, but I'm fine using that notation. So this one is N of T because it's number of bacteria, number of mice, number of people, N. And this is M of T, because it talks about mass. So this is the mass, and this is the number. Both models have what is called the initial number or initial mass. That is always N0 or M0. Both models have E, the Euler's number. Both numbers have R, which is the growth rate, T, but the decay has the negative RT. That's the reason why I would like to present the models together so you can see the difference. You do not have to memorize the models. I will give you the model. The function will be given to you. So one more time, what did this represent? Number of people, mice, bats at time t. The initial number of fish in the lake. The growth rate of the fish in the lake. And time t. I don't know, it can be in hours if it's bacteria, it can be in years if it's fish, who knows? What about this? Here we're talking about the mass.
So the t's are not the same.
They are the same.
Or they are
This t is time t, and this is t time t. Both of them either in minutes, both of them either in hours or years or seconds, but they are the same, of course. This one, the mass of substance today is how much we had initially, the decay rate, how fast it decays, it diminishes, and time is the same. It can be in years, in hours, in minutes, in seconds, and so on and so forth. The logistic function, there are so many different ones. I will not even think of a particular one. I'm just going to show you a couple. Here's one. Here's another. Don't worry, no one will test you on, but I just want to put one function in here. I'm going to copy one, p of x, so you can see one. You do not have to memorize any of these. As you see, this one has nothing to do with the previous ones. Totally different. It's called a logistic growth model or logistic function. All we have to understand is what these represent. Nothing else. Okay. So I like to work on problems with exponential growth, a problem with logistic function, and then come back to decay. Ready? Okay. Don't get scared when you see the way your book presents the model. It's fine. Okay, let's look at problem 8 on page 529. All problems in this section are pretty similar. All of them will ask us the same type of questions. Okay? Nothing fancy. Initially, as you know, the first problem, it will look difficult and long. But then the second and the third and the fourth will be okay. In the year 2000, the population of the Palestinians in the West Bank, Gaza Strip, and East Jerusalem was approximately 3.2 million. And by 2050, it is projected to grow to 12 million. Use the exponential growth model, which will be given to us. N of t equals n0 e to rt. Now be careful because my math lab will definitely use the notation in the book. Let me show you the notation in the book. Do they use R? No, they use K. Everything is the same. So this is the amount, or number, instead of n, number. This is A0 instead of N0, the initial number. And this is K instead of R, which is the same thing. Yes?
Why are they like, is this just like universal, you can use whatever letters you want?
This is universal. This book presents this. It's up to you. They are the same.
Okay. So K and R and A and F and are the same.
Yes. So these two are the same,
Yeah.
and these two are the same. And R is K. Okay, so first question. In which T is the number of years after, okay, T, number of years since year 2000. Okay, Use the exponential growth model, okay, in which t is the number of years after 2000, yes, to find the exponential growth function that models the data. So we are asked to find the model. I'm asked to find this model if you want, or this model, it doesn't matter. What don't I have? So remember, a is the function. It's f, right? Or n. T is the independent variable. So these are not variables. These are not unknowns. What is unknown is this number, which I don't have. And what is unknown is this number, which I don't have. Once I find this and this, I know the model. Because the model,
You do have M or A, M of 0 and A of 0.
yes, how much?
3.2.
Yes, it's true. So we are told that initially in year 2000, right, t years, number of years since 2000, the population was 3.2. So when t equals 0, because t equals 0 for the year 2000, the initial population is 3.2. So I know this or this, whichever you prefer to use, whichever model you want to use. So for now, I have that the number of people in the West Bank and Gaza Strip and East Jerusalem, 3.2 million times e to RT. So I already made use of this information. I have one more piece of information that I have not used yet. What is it? Say it again. No. I use this and I'm done. I did not use this. What does this represent? What does this say? When t is 50, comma, f of t is, that's it, 12 minutes. Very good. So one more time for everyone to see. Can anyone give us the ordered pair one more time?
50.
Yes. Why did you choose 50 as the x coordinate?
Time is always X.
Very good. Time is always independent. 50, comma, 12. Awesome. So now teach me how to put this ordered pair in the model that I have. I want to put this ordered pair carefully in the model I have.
T
What is this? No, I have to replace it. 12 million equals, awesome. 3.2, awesome, times E.
R
Yes?
50.
Exactly. R times 50 or 50R. Very good. That's all I needed. That's all I needed. What am I going to solve for now? The other thing that I didn't have for R. Is that clear? Yes? What do I have to do first? Say it again. Yes, I have to divide both sides by 3.2. Why? Because I have to clean it up. I cannot apply log to both sides yet. It's not cleaned up. Very good. So I divide both sides by 3.2. You don't actually have to divide. Just write 12 divided by 3.2 equals e to 50r. That's all I need. So now, like we just did a few minutes ago, I have two numbers that are equal. And I'm going to apply to both sides the same thing that will allow me to bring this down. And there is only one function that has that property that will allow me to bring the power down. Yes! Which is the inverse function of e to blah, blah, blah. Awesome. Very good. Well done. So two numbers are equal. Their natural logs will be equal. Very good. Awesome. The left-hand side is natural log of 12 over 3.2. The right-hand side is 50r times natural log e. But how much is natural log e?
One.
1. Let me show why. Okay. So let's say we want to find natural log e and we have no idea what this means. So I know that it can be changed into an exponential equation. What is the base? I don't see any base here. What is the base of ln? There is no base of 1, remember? It's e. E raised to which number is e? Should I say it again? Yes? Is this okay? You can plug in the graphing calculator anytime if you want. You will get 1. Or just say e raised to what number is e? Good. So then this is times 1. Or from here, r equals this over this. Natural log 12 over 3.2 over 50. Ready? Okay. So natural log, in parentheses, 12 divided by 3.2. Close the parenthesis and further divide by 50. So the growth rate is 2.6. However, we have to write it as a decimal number, and it has to have 4 decimals. All rates, please remember, 4 decimals. So r equals 0.0264. So now can anyone dictate the model? I want to write the entire model, n of t, because that was the question. We were able to determine the initial population in the year 2000, and now we will also we're able to determine the growth rate. So, can anyone dictate the model, please?
Three point
3.2 times e. 0.264. T indeed. Without t, I will not have the independent variable in there. Very good. Awesome. Okay, part B of this problem. In which year will the Palestinian population be 9 million? In which year the population will be 9 million? Say it again. Very good. N of t is 9, indeed. Equals 3.2 equal to 0.0264 t. Awesome. How do I determine when? What do I have to do next? Very good. I divide by 3.2. Yes. And how much is ln e? 1. Natural log 9 over 3.2 equals 0.0264 t. And finally, t equals natural log of 9 over 3.2, 0.0264. You understand how important it is not to calculate step by step, but wait till the final simplified form at the very end and plug everything in one step. Is that clear? Okay. Any questions from me here, please? Any questions? Okay, so we have natural log of 9 divided by 3.2. Close the parenthesis and divide everything by 0.0264. So in 39.2, what? Yes. In 2039, it appears that if the model still holds, it appears that the population will increase to 9 million. Okay, let's look at a logistic growth model. Okay, so we just copy that one, P of x. So these are problems 43 through 46 on 531. Any questions?